All right, this is Chapter 8 Summary Notes on the Gas Laws. This video will cover Boyle's Law. Boyle's Law states that pressure varies inversely to volume. So when the temperature and the number of moles are kept constant. So before, in a previous video, we pointed out that the ideal gas law is one law that all the other gas laws are derived from. All right, and this particular gas law is Boyle's law, which is pressure and volume varying inversely with each other. The number of moles are kept constant, temperature is kept constant, and R is a constant. All right, so this involves one set of conditions, but when we set one set of conditions equal to another, all right, this sets us up for being able to predict a variable if we know 3 out of 4 of them. All right, so in the picture you see here a piston with 1, 2, 3, 4, 5, 6 molecules of a gas in the left piston, still 6 in the right, but you notice that the atmospheres have doubled, okay, and the volume has halved from the first set of conditions. All right, but the thing is, the pressure times the volume for either set of conditions has the same answer. 1 times 4 is 4, 2 times 2 is 4. So there's a constant that occurs between the first set of conditions and the second set of conditions. All right, so that's why we can work gas law problems when we do this. Other nice thing about this, since it's an inverse relationship, we know that if pressure increases, the volume decreases, and we can predict how our answer is going to be, okay? Or which direction our answer is going to take. Or we do need to make sure that our units are the same for the pressure or for the volume. All right, but in this first particular problem, which deals with Freon, we're looking at what is the new volume of 8 liters. So our first volume is 8 liters. It's initially at 550 millimeters of mercury. So it's always good to assign your variables. All right, and then P2 changes to 2,200 millimeters of mercury. And again, they're emphasizing the fact that the temperature and the number of moles, the number of particles in there has not changed. Okay, I'm just trying to get my mouse so I can get some more room to work the problem. All right, so if we know those are our variables and we need to solve for the second volume, let's make a prediction. All right, pressure is increasing, 550 to 2,200. It's almost quadrupling. All right, so we know our volume needs to decrease by that same factor, the inverse of that factor. All right, so we have 8.0 liters times 550 millimeters of mercury, okay, is equal to V2 times, now you can choose to rearrange your formulas prior to working the problem or after you just do the substitution. And I'll model both as we go through these problems. Obviously we need that 2,200 on the other side, so if I divide both sides by that quantity, I can clear the term. Okay, it might be easier to clear terms prior to rearranging the formula. Okay, or I'm sorry, we want to rearrange the formula prior to substitutions. All right, so we'll bring up our calculator and plug this in, and we're looking to see if our volume will go down. So let's make a little down arrow here for that prediction. All right, so we have 8 times 550, and then divided by 2,200. And our volume does decrease to 2 liters. Don't forget to give back the correct amount of significant digits because your calculator displayed doesn't know about significant digits, but you do. We have 2 in the 8.0 liters, so we need 2 in the final answer, and it looks like we got it. Okay? and it does indeed decrease by 1/4 of the original volume. All right, so let's take a look at this next problem. Okay, and let me just move the calculator out of the way a little bit. It says a sample of oxygen gas has a volume. All right, so let's assign our variables as we go. 2.0 liters at a pressure of 600 mercury M&Ms. And it wants to know what the new pressure is if the volume changes to 36. All right, well, I think you can see that 12 and 36 increases by a factor of 3. So our pressure, our pressure should decrease by the inverse of that factor. In other words, it should drop to 1/3 the initial factor. All right, so our pressure should decrease. And we can show that this problem should go down to 200 millimeters of mercury. But I want to show you another trick of working these problems. That'll come up in another video, and that has to do with how you present your formulas. All right, but let's go ahead over here to the calculator. Just a moment. All right, and then we're going to divide by our V2, which is 36.0 liters. And we know that's going to be 3. We know that's going to come out to 200. All right, so we don't really need to do that on the calculator. Okay, you can see how that works. All right, now let's take a look at a conceptual problem. This stuff would quit bouncing around. All right, so we have some helium gas inside this canister, and it says cylinder A or cylinder B represents new volume. All right, N and T are constant, so we have the same number of moles and the same temperature. If pressure drops, what's going to happen? If pressure goes down, remember our predicting abilities, volume needs to go up. All right, so that should be B. So if pressure increases, volume should decrease, and that will be A. Okay, so you can do some predicting. All right, so here's another quickie problem. All right, I'm going to ask you to stop the video and work it. All right, come up with your answer, and then you can come back and see the work. All right, and check your solution. All right, so if you look at your screen, you'll see that I've circled the 240 mLs. And when we take a look at our variables, our volume 1 is 120 mLs. Our pressure is 850, and it drops to 425, so it halves. The pressure decreases by half. So if we remember about our predicting, if pressure goes down, volume should go up by the inverse of that factor. So the volume should double, and it indeed does. 425 into 850 is 2, times the 120 is 240. All right, so that's what I mean by a conceptual problem. You can predict and work it without your calculator. All right, and we have one more conceptual problem to take a look at here. And again, use your prediction powers to make that answer. And I'll stop the video and all right, you can check your screen here, and I hope that you deduced that the initial volume will go down, and it actually halves, as the pressure is increasing from 0.7 to 1.4, so you can see that it is doubling. So when we put it in the formula for finding the second volume, we can see that it does reduce to a 2 in the denominator, which results in 3.2 liters of volume, which cuts the initial balloon volume in half. All right, so I hope you know how to do Boyle's law now, both mathematically and conceptually.